Number 43. Repeat example 10.15 in which the disc strikes and adheres to the stick 0.1 meters from the nail. All right, so here's a picture over here, and here is the example. Here's a very quick, though, picture at the bottom. So we have a certain disc. It's traveling and going to hit this stick in black that has a pivot point right here. The mass of this disc is going to be 0.05 kilograms. They told us it was 50 grams, so I just converted it. And the initial velocity of this disc is 30 meters per second. The rod is initially at rest. And the rod is 1.2 meters long, and the rod weighs, no, I shouldn't say weighs, the rod has a mass of 2 kilograms. So basically what's going to happen, right, if you think about this, you know, as the disc makes impact with our rod here, the rod itself is going to begin to rotate, right? And it said that the disc is going to stick to the rod. So as the disc hits the rod and the disc will begin to rotate, all right? So what we need to do here is the first question for letter A is to, they ask us, what is the angular velocity of the two after the collision? So this one is a little difficult. You have to be able to conceptualize this properly from at the beginning. I mean, just like every problem, but this one's a little more challenging. How do you conceptualize it, right? You might say, well, I know I have some momentum initially, just from the disc itself, right? And you might say, well, this initial momentum should equal the final momentum, and that final momentum, oh, right, it's the angular, momentum. So so basically what you're saying is the initial linear momentum would equal the final angular momentum. And that, unfortunately, that's not a conservation. All right, that's not true. So the way you can kind of think about why that's the case, think about the height at which this disc hits the rod here. It basically depends, right? The higher this disc makes contact with the rod here, the further away, I should say, from the point of rotation, the faster this system will rotate after the collision, right? That's because essentially there's more torque, right? The further you go on up because the lever arm is getting longer, blah, blah, blah. Anyway, not to belabor the point, but the thing is that the distance this disc is from the pivot point is very important, right? It's basically a function of that. So how we can simplify this then is I'm going to use the conservation of momentum, okay? Angular momentum, that is. And I'm going to say that the initial angular momentum equals the final angular momentum. And now you're going to say, well, wait a minute, initial angular momentum? I mean, initially, before the puck or the disc makes contact with the rod, nothing's rotating. And yes, you are correct. However, I'm going to take the point of the initial point at like the almost infinitesimally small time frame right before this disc makes contact with the rod. Okay, so I'm going to, at that point, a fraction of a second later, it's going to start rotating. So I'm going to calculate the angular momentum of this disc as if it were to begin to rotate around this axis, but right before it makes impact with that rod. Okay, so that being the case now, right? Just to give you some framework here, and then the final angular momentum will be the combined system, right, of the rod here that will be rotating with the puck that's stuck, this whole thing as it rotates, okay? That's the final scenario. So expanding on these now, I have the moment of inertia of the disc by itself multiplied then by the angular velocity of the disc by itself, right? And then the final angular momentums would be a function of the moment of inertia of the total system now, which is the disc plus the rod. Okay, I'll just call it dr, disc and rod, multiplied by the angular velocity of the disc and the rod. We are after this variable, so simply just manipulate the equation now for that. Omega dr is equal to id omega d all over idr. Okay, so now from here, I need to calculate these three quantities. So I can expand on them now, right? I can substitute formulas in there. So the final angular momentum here of the entire system will be equal to the moment of inertia, the moment of inertia of the disk itself. Right? Now think about this. Here's the axis of rotation. The disk is basically going to be a point mass here that's going to rotate around the center. Okay, so the model that best approximates it is going to be this hoop, okay, where the mass is located at a certain distance from an axis of rotation, and that mass is located on the periphery, okay, of the rotation there. So this is then going to be the mass of the disk multiplied by the radius of the disk squared, okay, and then, that sounds great, and then now multiplied by the angular velocity. So the angular velocity now, we have to think about, we don't know the angular velocity, but is there a relationship maybe between linear velocity, aka tangential velocity, that I might be able to plug in here? And there is, right? Remember this equation, that the tangential velocity is equal to the radius multiplied by the angular velocity. And therefore, the angular velocity is equal to the tangential velocity over the radius. Now that's what I'm going to plug in here. Okay? So now I have the tangential velocity, which is just the linear velocity. That's all that is. Divided now by the radius of the disk. And that's it. I was like, is it squared? No, it's not squared. And then divided now by the total moment of inertia of the entire system. So now the total moment of inertia will be the moment of inertia for the disk itself, which is the mass of the disk, multiplied by the radius of the disk squared, plus the moment of inertia of the rod. And the rod here is best approximated by this figure, where it's basically a rod rotating about an axis on one of its ends. Okay, so that's going to be now the mass of the rod multiplied by the length of the rod squared all over 3. And now finally I can plug everything in, right? This problem is going to be fun. And I can also simplify some stuff, right? I mean, that simplifies, like if I wanted, whatever. Let's just plug everything in. All right, so the mass of the, let me give myself a little more space. So the mass of the disk is 0.05. The radius of the disk, meaning the radius from the axis of rotation, right? The distance from the disk here relative to the axis of rotation, that was 0.1 meters. All right, that's then multiplied by the tangential or the linear velocity, so that was 30. And this is now all divided by 0.5 times 0.1 squared plus the mass of the, so this is going to be 2 multiplied by 1.2 squared all over 3. I know I'm towards the bottom of the screen, but yeah, this problem is a doozy. So 0.05 times 0.1 times 30. And then divide that whole thing now by 0.5 times 0.1 squared plus 2 times 1.2 squared divided by 3. What do we get? We get about, so where should I put this? I'll write it over here. I'm going to have to erase everything though. All right, so just a heads up. So the final angular velocity of this whole system is going to be about 156 or so? 155, 156. And that is radians per second. So there's the final answer for part A. Okay, I'm going to maybe take this though and just bring this on up over here. All right, so we have that answer. We might need it later. All right, and this is just wonderful now. Sorry guys, just give me one quick second. I need like 3 computer screens to do this problem. All right, so that's up there. Okay, so now let's get rid of all this. And let's move on to now letter B. All right, so now letter B. I'll change the color, why not? Letter B. So now it says, what is the kinetic energy before and after the collision? All right, this one isn't bad. So before the collision happens, we look at this as everything is purely linear, right? I mean, there's no kinetic energy for the rod. It's not rotating or moving linearly. And the only thing that's happening is this disk is moving linearly. So before the collision, KE before is simply going to be equal to the kinetic energy of just the disk before. All right. So that means that the kinetic energy of the disk is simply 1/2 times the mass of the disk multiplied by the velocity of the disk squared. Okay, and we can just plug this one in now. Kinetic energy of the disk is going to be equal to 1/2 times 0.05 times 30 squared. So KE of the disk will be 0.5 times 0.05 times 30 squared. And we get a value of about 22.5. Okay, so 22.5 joules. Great. That's that answer. So that's for letter B. What I'll do is I'll take this again and we'll bring it up to the top, resize it, make it a little smaller. And we'll bring it on up there for now. Okay, great. Let's erase this. Now it wants to know after the collision happens, but after the collision, what's the nature of the motion? It's a rotational motion after the collision happens, right? The disk is going to get stuck to the rod, and the disk rotate around this point. And therefore, I'm going to now use my rotational kinetic energy formula. So KE of rotation will equal 1/2 multiplied by the total system's moment of inertia multiplied by that angular velocity of the system squared, okay? So this is KER is equal to 1/2. So we already calculated the moment of inertia, right? The total system moment of inertia to get I before, so we can find the angular velocity. It's in my calculator somewhere. I don't really remember what it is, but so let me just write this out. I'm not going to go through all the details though of it. It's just the mass of the disk times, I'm using these two formulas, right? Times the mass of the disk multiplied by the radius of the disk squared plus the mass of the rod multiplied by the length of the rod squared all over 3. That takes care of that. Then multiplied by our angular velocity squared, okay? So that's just omega dr squared. And let's just plug everything in. So KER is 1/2. Mass of the disk was 0.05. The radius was 0.1. That's squared, plus then the mass of the rod was 2 kilograms, 1.2. Now this is squared, all divided by 3. And then just multiply it by the 0.156 squared. And let's see what we get. So KER is equal now. So 0.05 times 0.1 squared. I'm doing the moment of inertia first, plus 2 times 1.2 squared divided by 3. Multiply that now by 0.5 and then 0.156 squared. What do we get? We get a value of about 0.0117, it looks like. All right, and that's again in joules. So that takes care of that answer. All right, let's save that, resize it, make it a little smaller, and let's bring it on up here. Okay, good so far. All right, we're almost there. So now letter C, right? Oh, joy. Letter C. What is the total linear momentum before and after the collision? Okay, so before the collision happens here, the only momentum that's the only object that has momentum is the object that's moving, right? It would be the disk. So this is easy. So the momentum before the collision is equal to the momentum of just the disk. Okay, so the momentum of the disk is equal to the mass of the disk, right, multiplied by the velocity of the disk. The momentum of the disk is then equal to 0.05 times 30. That's easy. PD is equal to 0.05 times 30. It should be like 1.5. Yeah, 1.5. So this is 1.5, and it'll be in units of kilogram meter per second. All right. So that takes care of that one. All right. And I'm still going to bring this on out, resize. There we go. Bring the answer up there. Okay, great. And now let's calculate the momentum after. And this one is a little harder because it says linear momentum after, but you might be thinking to yourself, wait a minute, linear? The system after is rotating. What are they talking about? We'll try to make head. We'll try to understand what they want. All right. So this part is a little trickier, and let me actually just redraw this down here. So here we have the rod, and here will be the got the disk on it. Okay. So after the collision happens, this thing will begin to rotate, right? Now, I should have probably actually drawn it. Let me draw this vertically for now. Just make it a little easier. Okay, great. And then here's the ball. Pretend it's touching. I'll move it over. There we go. And the axis of rotation is at the bottom. Okay, remember these distances are going to be important. The disk is about 0.1 meters away. Okay, and the whole rod is 1.2 meters long. All right. So 1.2, let me write that a little neater, 1.2 meters long. So now, in terms of the linear velocity, what we need to do here is remember, after these two make contact, it's a rotating problem. All right, the system is rotating. So if you want to go from rotational concepts back to linear concepts, you have to know the formula to get back, right? This is the formula that does it for accelerations, and the same formula or similar structure, right, is the one to do it for linear, for velocity, I mean. So you have the tangential velocity equaling the radius of rotation multiplied now by the angular velocity. Now, no matter where you are on this system, the angular velocity is the same, okay? We've talked about that in prior problems, all right? So the angular velocity is the same no matter where you are, but the tangential velocity is not, okay? So essentially, right, I can rewrite this now if I'd like. I can make this VT over R is equal to omega. And what this says is that if this is constant, right, if the angular velocity is constant, that means as the radius goes up, the velocity also goes up. And that's what we expect, right? As you move further away from this axis of rotation, the velocity at which you would be traveling is actually going to increase, right? It's like, you know, if you think about it, the Earth, right? You're rotating fastest around the equator, slowest at the North Pole, etc. All right. So now we need to use this concept in order to try to find the total linear momentum after the collision. Now, knowing that this is a rotational problem, it's best to now think about this in two pieces. One, we'll talk about the disk, and two, we will talk about the rod. So let's talk about the momentum after for the disk first. Okay. So momentum is simple, right? I mean, momentum is mv. Okay. So the momentum after for the disk would be equal to the mass of the disk, right? After, I mean, it's the same as before, multiplied by the velocity after. This is the linear velocity, okay? Not the angular velocity. So that's the big hint, okay? We don't have the linear velocity, but we do know the angular velocity of it because we calculated that before. And we also do know the distance that this disk is relative to the axis of rotation. So we also do know r here. Okay, so basically I'm going to do a substitution here. Throw that on in. So this is PA is equal to MA times R omega. And now I can calculate for A, okay, meaning for the disk. Okay, so this is the momentum after for the disk is going to be the mass, so 0.05 multiplied by the radius, which was 0.1, multiplied by that angular velocity, 0.156. And we have here, so 0.05 times 0.1 times 0.156. So we get about 7.8 times 10 to the minus 4. Now let's put this answer aside for now, okay? This is just the momentum of the disk after. Now what we have to do, I'll leave it right here. Now what we have to do is talk about the momentum of the rod after. Okay, so again, we're going to look at it separately. All right, so now let's talk about the momentum of the rod after. And again, we have the same idea, right? Momentum of the rod after should be equal to the mass of the rod multiplied by the tangential or the linear velocity of the rod, okay, after the collision. All right, let me just call this A for whatever. Okay, so now, again, we are in the same situation, okay? We know the angular velocity, we understand what the radius is, so what we can do is we can do a substitution. It's just going to be very critical what we use for R here. So the momentum after is going to be equal to the mass of the rod multiplied by the radius of the rod multiplied then by the angular velocity. Now the radius, this is the part that you have to, what we are talking about here in terms of the mass, right? The mass of the rod here is going to be 2 kilograms. But where is this mass located? Like, it's over this whole thing, right? It's distributed over the whole thing. Remember, we treated the disk as a point mass. So this was easy because the point mass here of the disk was located 0.1 meters away. But now, this whole rod, in which the weight, or the mass, I should say, is evenly distributed over the entire rod here, what's the radius then? Right? If you say the radius is 1.2 meters, then you're only taking into account the mass that's all the way at the extreme here. You're neglecting all of this. And then if you say it's nothing, then obviously you're neglecting the rest of the mass, okay, at the other end. So doesn't it kind of make sense that we probably should take the average, right? So that's the whole idea of center of mass. Okay, so what we have to do is we have to use the R value here of the center of mass. Okay, so when we do this, the radius is going to be half the center of mass, right? If it's a uniform rod, which we can assume it is, we can simply then realize that the center of mass is going to be symmetrically located at the halfway point. Okay, so it'd be 0.6 meters. All right. Or, another way to write 1.2 divided by 2. All right. Now, knowing that, we can plug it all in. So PA is equal to the mass of the rod, which was 2 kilograms, multiplied by the radius, which was, as I mentioned, 1.2 over 2, multiplied then by the angular velocity, and that's 0.156. So let's get this now. What does this come out to be? So this is, the 2's would cancel. So it's 1.2 times 0.156. Almost made a calculation mistake there. So this works out to be now 0.1872. Okay, now this is for the disk, and this is for the rod. So guess how do we find the total? I think I actually heard you through the computer. We add them together. All right. So take the values, add them together. 7.8 times 10 to the minus 4, and voila. So here we have the total momentum after now. Total momentum after will be this answer. It will be 0.188. It looks like 188 kilogram meter per second. Whew. Guys, thanks for tuning in. That was a fun one. All right. If you had as much fun as I did, hit that subscribe button and the like button too. That would be awesome. And if you could tell some of your friends about what we're doing, that would be great. Much appreciated. And I'll see you in the next question. All right. Take care.